Hello everyone, today let's take a look at a pretty cool question, Quantipus number 125, where we're playing rock, paper, scissors. However, the catch is you can play rock, paper, or scissors, but your opponent cannot play rock, so they can only play paper and scissors. And every time you win, you make $1. Every time you lose $1. And every time that there's a draw, nothing happens. So part A is asking, what is our expected profit per round, assuming that both people play optimally? Okay, this is me. I'm able to play rock, paper, and scissors. This is my opponent, who's only able to play paper and scissors. And obviously, I'm going to have a little bit of an advantage because I have more options than my opponent. Okay, so I want to play this game optimally, so I want to maximize basically the expected profit that I make per round. Okay, so to write it out, me playing optimally means that I want to choose the move that maximizes my expected profit. So first of all, let's make a table. I can play either rock, paper, or scissors, so this is me up here, and then this is my opponent down here who can only play paper or scissors. Now let's go through every possible outcome, right? If I play a rock and my opponent plays paper, well then paper beats rock, so I'm going to lose $1 here. Now if I play rock and my opponent plays scissors, well rock beats scissors, so I'm going to make $1 here. Okay, so now let's keep going. If I play paper and my opponent also plays paper, well then that's going to be a draw, and in a draw nothing happens, so I make $0. If I play paper and my opponent plays scissors, well then I'm going to lose, so I'm going to lose $1. If I play scissors and my opponent plays paper, well then I'm going to make $1. And if I play scissors and my opponent plays scissors, then it's going to be a draw, so $0. Now my opponent is also going to play this game optimally, so if I chose a pure strategy like just play rock every time, well then my opponent's going to see that I'm doing that, and they're going to exploit me by just playing paper every time to counter, right? Similarly, if I chose to play paper every time, well my opponent's just going to counter that by playing scissors every time. Similarly, if I chose to play scissors every time, then my opponent would just counter me by playing their scissors every time because, well, they don't have a rock, so the best I can do is have a draw when I play scissors every time. So obviously a pure strategy is not optimal, so we're going to want to do some mixing, right, with probability. Some probability that I play rock, some probability that I play paper, some probability that I play scissors. Also, obviously my opponent is playing optimally, so they do not want to play a pure strategy either, because if they chose to play paper every time, I would counter by playing scissors every time and just make $1 every single round. If they chose to play scissors every time, then I would counter by playing rock every single time, and then I would make $1 every round as well. So because my opponent's playing optimally, they're going to have a strategy that looks something like this. They're going to be playing paper with some probability Q, and then they're going to be playing scissors with some probability 1 minus Q. Okay, so I know their general strategy now, and I want to choose the move that maximizes my expected profit based on this. So what is the expected value of me playing a rock? Let's do that one first. So now my expected return when I play rock, well, I'm going to lose $1 when they play paper, and they're going to be playing paper with probability Q, so I'm going to get -1 times Q, and then I'm going to also make $1 when they play scissors with probability 1 minus Q, so I add on 1 times 1 minus Q. Okay, so now what's my expected return when I play paper? So the expectation of P, I'll say. Well, if I play paper, my opponent's going to be playing paper with probability Q, and then I'm going to make $0, so I have 0 times Q right here. Then when my opponent plays scissors and I play paper, well, I'm going to lose $1 with probability 1 minus Q, so -1 times 1 minus Q. So now finally, if I play scissors, well, they're going to be playing paper again with probability Q, so I'm going to make $1 Q% of the time, so I'll say the expected value of scissors is going to be 1 times Q, and then I'm going to make $0 1 minus Q% of the time, so plus 0 times 1 minus Q. So if I simplify this, my expected return for rock is going to be 1 basically minus 2Q. My expected return for paper is just going to be -1 minus Q, also known as Q minus 1, and then my expected return for scissors is just going to be Q. So on any one of my turns, I want to choose the move that maximizes my expected profit, so I'm just going to take the maximum on any given turn. Let's say I know what my opponent's Q value is, I know what their distribution is, well then I'm just going to take the maximum of 1 minus 2Q, Q minus 1, and Q. So for instance, just by playing this game for a while, if I found out that my opponent's strategy was just to play paper every single time, so I have Q equal to 1, and then play scissors 0% of the time, so this would be 0 obviously. Well, if I figured that out, my expected return for playing rock would just be 1 minus 2 times 1, which would be -1, right? My expected return for paper would be Q minus 1, and Q is 1 in this case, so this would be 0, and my expected return for playing scissors would be Q, so 1. So now I would choose the move that maximizes my expected profit. In this case, that would be scissors, and that makes sense, right? Because they're playing paper every time, I'm going to counter by playing scissors every time. But now my opponent's playing optimally, so they're obviously not going to want to do that. In fact, they're going to know that I'm going to be using this strategy because they are playing optimally, right? They know that I want to take the move that maximizes my expected profit, so they know that I'm going to do this. So because they know that I want to maximize my expected return, they're going to take a value of Q such that the maximum value out of my 3 options is minimized. So again, one more time, my opponent is going to choose their own strategy, and they're going to play optimally, so they're going to choose their Q value such that this function right here is minimized because they know that I want to maximize my expected profit per turn. So now the question is, what value of Q are they going to choose? We're basically minimizing the maximum of these three functions right here, right? 1, 2, and 3. So let's plot this out. I have Q down here on my x-axis, and then on my y-axis is going to be my expected return based on this value of Q. So first of all, for rock, I have this function right here, so I can plot that. Basically, it's going to look something like this. It's going to intersect the x-axis at exactly 1/2, and it's going to start up here at the coordinates 0, 1. Now my expected return for paper is Q minus 1, so when we plot that out, it's going to look something like this. It's going to intersect the y-axis at 0, -1, and then it's going to come up here and intersect the x-axis at 1, 0. Okay, this point right here should be 1/2, 0, and now what is my expected return for scissors when plotted out? Well, it's going to just look like this. It's just equal to Q, so we're going to have this point right here, which is going to be 1, 1, and then right here is obviously the origin, 0, 0. My opponent's looking at this graph. They're seeing the probability that they play paper on this x-axis and my expected return on the y-axis. Now my opponent's looking at this graph and they're thinking to themselves, well, if I choose Q to be 1, so I play paper every single time, well, then they know that I will just exploit them by playing scissors and making $1 profit on them. And then they're also thinking to themselves, well, if I choose Q to be 0, well, then they know that I'm going to exploit them as well by making $1 profit on them when I just play rock every single time. Maybe they're also thinking, what if I choose Q to be, let's say, like 0.1, so something right here? Well, if they choose this strategy right here, again, I'm just going to be exploiting them by playing rock every single time, because if I plug in Q into this equation right here, my rock equation, I'm just going to get 1 minus 0.2, so 0.8, so I'm just going to be expecting to make 0.8 on every single turn. Basically, what's going on here is that no matter what value of Q that they choose, I'm just going to be choosing the maximum among all three of these functions right here. For instance, if they choose their Q to be right here, well, then I'm just going to play scissors every time. This is my scissors line, this is my rock line, and this is my paper line, by the way. So if they choose Q right here, well, in the long run, I'm basically going to be able to figure out what percentage of the time that they're playing paper so I can understand their Q value, and I'm going to adjust my strategy, but just by playing scissors every time so I can make this much profit on them every single turn. Okay, Q is a probability, so we know that Q has to be between 0 and 1, so this is basically the range of values that my opponent can choose for their Q value. And they want to, again, minimize the maximum of these three functions right here. So what is the maximum at every single point between 0 and 1? Well, right here, it's going to be this function, that's the maximum, and then it's going to switch at this point right here, and it's going to become this one, that's the maximum. And the minimum of this green maximum function is just going to be this point right down here, obviously the intersection point between my rock line and my scissors line. Also notice that paper is always either a losing strategy or a break-even strategy, so I'm just never going to be playing paper because I have better options in rock and scissors. Okay, so now my opponent is going to be choosing this Q value right here, because when they choose this Q value, my expected return is going to be minimized because, again, I'm choosing the maximum of these three functions. This is what the maximum looks like between 0 and 1, and this is the minimum point right here. So this is the Q value that they will choose. So at what Q value do these two functions intersect? My two functions are 1 minus 2Q and Q. So I set 1 minus 2Q equal to Q, and now I can just solve for Q. And when I do that, I'm just going to get Q equals 1/3. Therefore, the optimal strategy for my opponent is to play paper with probability 1/3 and then play scissors with probability 2/3. And then if they choose this Q value, my expected return for playing rock is going to be, well, if I plug in 1/3 right here, I'm going to get 1 minus 2/3, so it's just going to be 1/3. And then my expected value for scissors is just going to be 1/3 if I plug it in for Q right there. And obviously, if I ever choose paper, well, then I'm just going to be expected to lose 1/3 minus 1, so I'm just going to be losing 2/3. So why would I ever play paper, you know? So therefore, with both players playing optimally right on my turn, I want to choose the move that maximizes my expected profit. So in part A, it's asking us, what is your expected profit per round? Well, again, on any round, I'm just going to choose the move that maximizes my expected profit. In this case, the expected value of me playing rock is going to be 1/3. The expected value of me playing scissors is also going to be 1/3, and the expected value of me playing paper is going to be -2/3. So the maximum return that I can get per round is either when I'm playing rock or playing scissors, as they're both 1/3. Obviously, I'm never going to be playing paper, so the expected return on any given round is just going to be 1/3. So that answers part A, and now let's go do part B, which should be pretty simple now that we've done part A. Okay, so we figured out our opponent's optimal strategy, and when they play the optimal strategy, when we play optimally, this is our expected return. It's going to be 1/3, the maximum of these three. However, that was assuming that we were playing optimally, but we never figured out our own optimal strategy. We figured out that rock and scissors are our best options, so we should mix between them, but we never actually figured out this mix. For instance, if we just said, let's play rock 50% of the time and scissors 50% of the time, well, that doesn't necessarily mean that our return is still going to be 1/3. If I did actually choose this strategy, well, then my opponent could actually exploit me. And they would do so by adjusting their strategy. If they saw me playing rock 50% of the time and scissors 50% of the time, well, then they're not going to use this strategy anymore. They're just going to be playing paper 100% of the time. So if this was my strategy and then they adjusted by playing paper 100% 100% of the time, my expected return would no longer be 1/3. Instead, it would be, well, I have a 1/2 probability of choosing rock, and if they play paper every time, I'm going to lose $1 in that situation, and a 1/2 chance of playing scissors, well, I'm going to make $1 in that situation. So this is no longer equal to 1/3, right? This is going to be equal to 0, which is better for my opponent. So they're going to adjust when I play this strategy. So I still need to find the best distribution of rock versus scissors that I can play so that my opponent cannot exploit me, and that's basically what Nash equilibrium means. So I'm just going to do the same thing that I did before. I'm going to have some Q and some 1 minus Q are probabilities for rock and scissors. And again, now I'm going to look at it from my opponent's point of view so that I can see what Q and 1 minus Q value that I should choose. So this is my strategy over here, and if this is my strategy, the expected value of my opponent playing paper is going to be, well, right here, this represents my gain. So my opponent's gain in this situation would be +1, not -1. So when my opponent plays paper and I play rock with probability Q, well, they're going to make $1, not lose $1. So this is going to be plus Q, basically 1 times Q. Then when I play scissors with probability 1 minus Q, basically they're going to lose $1 here, not make $1. So we have to subtract off 1 minus Q. Well, the expected value of my opponent playing scissors, I'm going to play rock with probability Q, and in that case, they're going to lose $1, right? Inverse, so -Q. And then it's going to be a draw when I play scissors with probability 1 minus Q, so that adds nothing to our expected value. So again, now we have these functions. They're going to basically be, this one's going to be 2Q minus 1, and this one right here is just going to be -Q. So let's plot those. So again, this is what it looks like when you plot it out. We want to choose our Q value such that our opponent's gain is going to be minimized. You can see that when we choose Q equal to 1/2, well, then we're going to have a 0 expected gain, which we just showed. Now, actually, if we choose rock to play every single time, our opponent's going to adjust their strategy by countering by playing paper every single time, and then we're just going to be expected to lose $1 every single round. So our opponent's going to be choosing what to play based on the maximum of these two functions, which is just going to look like this phi right here. We want to minimize that, which is going to be at this point right here. And again, that's just the intersection of these two functions. When we set these equal to each other, I have 2Q minus 1 equals -Q. I can rearrange this to get 3Q equals 1, so Q equals 1/3. Therefore, for my optimal strategy, I'm going to want to be playing rock 1/3 of the time, basically, and that means I'm going to be wanting to play scissors 2/3 of the time. And then if I start to get tricky and try to do some type of deviation where I start playing rock more than 1/3 of the time, well, then my opponent's just going to counter by just playing paper every single time. And if I try to get tricky in the other direction and just start playing scissors a little bit more, well, my opponent's just going to counter that by playing their scissors every single time, and then my profit's going to be reduced. So these strategies right here are in Nash equilibrium, right? Because if I start getting tricky and start changing my strategy, my opponent's going to exploit me, and then if they start changing their strategy, getting tricky, well, I'm going to exploit them. So my optimal strategy is to play rock 1/3 of the time and scissors 2/3 of the time, and their optimal strategy is to play their paper 1/3 of the time and their scissors 2/3 of the time. This right here is both of us playing optimally. When we're both playing optimally, I'm going to expect to make 1/3 every single round. Now that we have the actual strategies, we can actually just explicitly calculate the expected value of a given round. We already know it's going to be equal to 1/3, but we can just check it. So I'll say the expected value of a round. So basically what's going to happen, well, we're both going to be playing scissors 4/9 of the time. And in that case, well, we're going to be making $0 here. 1/9 of the time, I'm going to be playing rock and they're going to be playing paper. In that case, when I play rock and they play paper, I'm going to lose $1. Now, if I play rock and they play scissors, which is going to happen 2/9 of the time, right? 2/3 times 1/3. So I play rock, they play scissors. That's going to be this row right here. I'm going to be making $1. So $1 2/9 of the time here. Now, finally, in the case when I play scissors and they play paper, which also happens 2/9 of the time, basically what's going to happen, well, when I play scissors, they play paper, we're going to get +1 as well. And this is all just going to simplify down to 3/9, which is just equal to 1/3.